So today I want to finish the chapter about the experimental Bell tests. And you remember we have discussed things like atomic cascades, where you emit a photon pair, parametric down conversion, where you also emit a photon pair, or Bell tests using ions, where you exploit the high detection efficiency. And I want to finish this chapter by discussing what people call loopholes. And that means that all of these experiments are not quite perfect like they should be for an ideal Bell test, and therefore, strictly speaking, they do not yet convincingly rule out the existence of local hidden variable theories that could underlie quantum mechanics. So let us discuss these loopholes. So essentially there are two loopholes, and the first one is simply the locality loophole and the other one is the detection loophole. So the locality loophole comes about in any experiment where you don't guarantee that there is no subluminal signal possibly traveling from one detector station to the other and telling one detector what has been the setting that you just chose at the other detector. So in order to fix this locality loophole, simply you have to have a large distance and be able to set your detector settings very fast and to detect very fast. Because then there is no way that even a light signal could possibly arrive in time at the other detector. So in order to close this locality loophole, what we really need is simply that the travel time of light during the time it takes to do the measurement is smaller than the distance between the two detection stations, because then there can be no signaling. And for example, we learned that this locality loophole in particular has been closed in those parametric down conversion experiments where you had this 400 meters separation of A and B on the Innsbruck campus. Okay, so the other loophole then that remains in those experiments is the detection loophole, because things are not as perfect as you would like them to be. In fact, typical photodetectors only have on the order of a few dozen % photo detection efficiency, and then there's still all the efficiency associated with collecting these photons. So overall you have relatively low efficiencies of actually detecting a pair of photons. And so in order to close that, in principle you would need better detectors. And we have seen that in the example of the ion trap Bell test experiment, one has practically perfect detection, because the idea is that you have state-selective resonance fluorescence and you scatter many, many photons. For example, in those experiments you would scatter 60 photons, and even if your photon detector is not really that efficient, you can make sure that either you see all those photons or you don't see anything, and so you distinguish those two states. But the unfortunate fact remains that no one has been able so far to close both of these loopholes at the same time. Now I want to spend a little bit on the detection loophole. For the locality loophole, basically all you have to do is to have a large distance or to be very fast. For the detection loophole, we can work out a little bit what it really means, what should be the threshold for the detection efficiency that you would need in order not to be spoiled by the detection loophole. And so, let's go back to the Clauser-Oldholm-Shimony inequality, and the basic quantities that we had here were those where you just take the outcomes at the two detection stations, let's call them A and B, and usually they would be plus or minus 1, and you take the correlator. Now, if I imagine for a moment that whenever I don't detect anything because somehow the photon got lost on the way or the detector was not good enough, I just assign the value 0. In that case, the observed correlator will simply be the ideal correlator multiplied by those detection probabilities, at least in the simplest possible model. So you would multiply it with eta A and eta B, and eta would be a number between 0 and 1, telling you how likely is it to detect a given photon. So we know that this Clauser-Bulltrausch-Shimony inequality stated that a certain combination of these correlators in local hidden variables was less than 2, or less than or equal to 2, whereas in quantum mechanics we found that the ideal value would be 2 times square root of 2, so it was larger by a factor of square root of 2. And now the nasty thing is that your detector efficiencies can reduce the observed values. Even if you start from quantum mechanics, they could reduce the observed values by a factor of more than square root of 2, and then you have lost, because then you cannot tell with certainty that indeed you ruled out local hidden variable theories. Maybe because these outcomes are simply consistent with local hidden variable theories. So if this product eta A and eta B is less than 1 over square root of 2, then in spite of starting from these very strong quantum mechanical correlations, you spoiled everything by having these bad detectors, and so you can't really observe the true violation of this inequality. And so, assuming for a moment that these efficiencies are the same at the two detector stations, you can work out what is the threshold for the detector efficiency. And you find that the threshold, well, this is the square of eta, so you take the square root once more, and you find then that the threshold would be 84%. And so you would need detectors better than 84% to avoid this detection loophole. And so at the moment, this is not yet achieved in these photonic experiments, because usually these detection efficiencies are on the order of 50% or something. Now, there is another issue in these experiments, because what you observe are not really probabilities. That would mean that you create your photon pair or your particle pair at a very well-defined time, and you know that it has been created, and then you look, is there a click or no? And so you would obtain a probability. But what you really do is you illuminate your source all the time with a strong pump beam, and then you have hopefully these signal and either beams, that is the split photon pair beams, going out from the source, and then you detect photons at a certain rate. So what you really see are rates. With a certain rate, for example, I detect coincidence clicks between the two detectors. And obviously this inequality, the Clauser-Bulltrausch-Shimony inequality, demands probabilities or demands correlators which are dimensionless. So even for dimensional reasons, you can see that you are not allowed to insert rates into this inequality. And so the question is then, how do you convert the experimentally observed rate into a probability? And that is not so difficult if we allow ourselves to just write down the simple relation between probability and rate. Because what would we do? We would say, for example, what is the rate at which you detect like A in state +1 and B in state -1, just to pick an example? Well, you would first have a rate at which you produce these photon pairs. That depends on the strength of your pump laser, the efficiency of your source. So let me call that R emit. That is the rate of pair emission. Then sometimes there might be a geometrical factor that some pairs are emitted in the wrong directions and you will never collect them in your optics at your measurement stations. So there will be a probability to determine this process. Let's call it P collect. Then you are going to measure things, for example, by running through polarizers, and the probability of getting this particular outcome, say at station A you have horizontal polarization, at station B you have vertical polarization or something like that, that will be determined presumably by your local hidden variable theory. At least that's the statement we want to test. So here you would insert your actual probability as calculated from the local hidden variable theory to obtain A equals +1 and B equals -1. And then you still have to multiply it by these detection efficiencies, so eta A and eta B. Okay, so that is probably the naive formula you would write down. And now you see that there's only one part of it which depends on your detector settings and on the measurement results, and that is this part. So under this assumption that this is really true, you can easily extract the probabilities by observing the rates. And so, for example, what we could write would be the following. We want to extract these probabilities, and how can we do that? Well, we have several weights at our disposal, the rate to get A equals +1, B equals -1, +1, +1, and so on, all the probabilities. And so, in terms of these probabilities, that should add up to 1. So I can get the common prefactor simply by adding up all these terms, and then I can normalize. So, for example, what would I write down? I would say, okay, P of A equals +1, B equals -1 is presumably the weight to get A equals +1, B equals -1, divided by something which is obtained by just summing all the different possibilities. Because then the probabilities inside here, they just sum up to 1, and I end up with all these prefactors, and so I can cancel these prefactors. So that's what I would do in a simple-minded manner. So here I would have the sum over all those 4 terms with all the 4 possibilities. And that's really a kind of expression you see applied in real Bell tests. So basically you normalize. You simply normalize to account for your low rate of emission, your low collection efficiency, and your low detection efficiencies. Now, this is certainly what you would always do because it sounds very plausible, but the whole point of Bell tests is that you are very skeptical. You're almost paranoid because you never really know whether nature, so to speak, is trying to trick you. And so you have to go back and ask yourself, what do I really assume when writing down expressions like this? And it turns out what you really assume is that these detectors, for example, don't conspire against you. For example, these detection efficiencies, they don't depend on the hidden variable parameter lambda. Yeah? They are independent of all these polarizations. It's just a photodetector that happens not to click even though a photon has fallen on the photodetector. And so as long as that is true, that's fine, because then what happens is you have this large stream of entangled particles and you just detect a small fraction, but it's a fair sampling of all the particles. And if that were not true, then of course all of this would not work. Extracting the probabilities in this way would not work. So people call this the fair sampling assumption. And so, just to state it in words, you could say that the detected pairs in their statistical properties are like a fair sample of all the pairs. Just in the same way that if statisticians want to find out something about the population of Germany, they try to also find a fair sample, asking 1,000 people who stand in for 60 million people. So what could happen in the worst case would be something like, in reality, the probabilities would be compatible with local hidden variable theories, but for some strange reason, the detectors conspire to produce, after throwing away many of the pairs, after throwing away many of the detection events, statistics that seem to be compatible with quantum mechanics. Yeah? So that would be the worst case. Now, there has gone a fair bit of thinking into these things because it's important for almost all experiments because they can't close the detection loophole. And it turns out that one can come up with a slightly weak hypothesis about what is going on. And that was found out by Clauser and Horn in 74. Their assumption is very, very reasonable. It says, look, if I have my polarizer in front of my detector, I get a certain click rate, I get a certain probability of detecting a photon, which unfortunately is lowered because of the finite detection efficiency. And now if I take out the polarization filter, then that should not mean that I decrease the detection probability. Or in other words, if I put in the polarization filter, I should not thereby increase the detector efficiency. That would sound stupid, wouldn't it? So that is their particular assumption, and it's called the no enhancement hypothesis. So again, in words, if I put in a polarizer, I do not enhance the detection probability. Sounds very plausible, and for example I can draw a little picture here. So the typical setup they have in mind is one where photons just go through a single polarization filter, and either they are absorbed in the filter or they pass through the filter. And so if I put in this polarizer, I don't actually enhance the detection probability. That's their assumption. And in the tutorial you actually went through an example where this no enhancement hypothesis would be violated, and then you suddenly find that if the detection efficiency is low enough, you can actually produce a situation where it seems like a Bell's inequality would be violated, but in actual fact you have a local hidden variable theory. Okay, so Clauser and Horn then, on the basis of this no enhancement hypothesis, were able to write down a modified Bell's inequality that is actually insensitive to the detection probability. So let me just write this down because this is a form that has often been used to interpret the experiments. So what we imagine is really a setup where at each of the stations we have a polarization filter that can be turned, and we detect only those photons that go through this polarization filter. And the idea is then not just to register correlations between these simultaneous clicks, but also to compare against the probabilities of clicks that you get if you take out the polarization filter. So that's the trick. And I can just write down this inequality, which involves the probabilities for simultaneous clicks at the two detectors. So imagine you have any small time interval, what's the probability to register simultaneous click at the two detectors? And that depends on the polarizer settings, which I denote by A and B. And then the inequality looks very much like the original CHHS inequality, only with these probabilities plugged in instead of the correlators. So you have these different combinations of settings. And And this is supposed to be less than or equal to not a definite number, but actually a sum of probabilities that result when you take out the polarizers. So that they happen to denote by P of A prime and infinity, which means what is the probability within a given time interval to register a simultaneous click at the two detectors if I take out the polarizer at station P? Plus a similar expression if you take out the polarizer at station A. Okay. So that is their modified Bell's inequality. And the nice thing about it is, if you have bad detectors, it doesn't hurt. Because you see, all these probabilities are multiplied by eta A and eta B, both on the left-hand side and on the right-hand side. So it really drops out in the end. Also, if I phrase it in this way, that I say this is the probability for simultaneous detection in a given small time interval, then on its own this probability would scale like delta t squared, where delta t is the time interval, but again this drops out. So both the left-hand side and the right-hand side scale in the same way with the detection probabilities, and so you don't care anymore. But again, there is this particular no enhancement hypothesis, and you learn that if this is violated in your model, then you can't say anything. So it is still of great importance to figure out ways to close both loopholes at once, the detection loophole and the locality loophole. And that's not so easy. For the detection loophole, people are betting on detecting the state of some ion or atom, because that seems to be the best bet. And then you have to think about how to close the locality loophole at the same time. So what I want to mention now is two experiments that are in the making and have been in the making for quite some time, a decade or so, which have the purpose of closing these two loopholes at once. So the first one I want to mention is a proposal by Frey and Walter. And it builds on the fact that if you take a mercury dimer, a molecule made out of mercury atoms, then the spins of the atoms are already in a spin singlet state. We initially discussed this for the hydrogen molecule, but it seems that for reasons of laser physics, mercury is really even better. And so then the idea is to split this with a laser. So the atoms fly apart. And then, by a combination of some lasers, you can ionize them, but in a state-selective manner. So only if the spin is up in some direction, you ionize it, and if it's down, you don't ionize. And the nice thing about ionization is that there are very, very efficient ways to detect the ion and the electron. So again, here comes a laser, or rather, even a combination of lasers, possibly, and you have this state-selective ionization. And so this has very high efficiency. It seems to be a very challenging experiment because there are many steps involved where you have to have the right lasers available and you have to have the right timing and so on. So this has been in the making for at least 10 years. There is another proposal and ongoing work, and that is by the Weinfurter group. And again, in the end, detection is by state-selective ionization, so it is supposed to be very efficient. Again, you have atoms, but instead of starting with a molecule where you already have an entangled state, these atoms are really kept separate in individual traps. So then you have to find a way to entangle the atoms in the first place. So let me first draw the level scheme of these atoms. These are rubidium atoms, and they have the interesting feature that in their electronic ground state, there are actually 3 hyperfine levels. And these will become important. So this is F equals 1 for the total spin, and so you have MF equals minus 1, MF equals 0, and MF equals plus 1. Okay. And so now the first step of this experiment will be, after you've trapped your atoms, that you excite each of the atom, and after the excitation it will decay. Okay? So obviously there are 3 decay pathways in principle, and they will lead to different polarization of the photons. Now I won't draw the pathway leading to MF equals 0. You can somehow forget about that, because any of those pathways has a particular dipole radiation pattern, and you just select only those photons that are emitted in directions where MF equals 0 does not contribute. You remember we had something similar for the cascade, for the photon cascade. And so now there are these 2 pathways left, and they produce photons with different circular polarization, because they also end up with a different spin state for the atom. And so let's call this sigma plus and sigma minus. That would be, say, right-hand circularly polarized and left-hand circularly polarized. And so what now happens is, initially you just start from the excited state, but after you fall down, either you have emitted a sigma plus photon and you are in state minus 1, or you have emitted a sigma minus photon and you are in state plus 1. And since these 2 possibilities are just as good as the other one, this is a coherent superposition of possibilities in quantum mechanics. So what you get is atom-photon entanglement. And so you would write down the state like this. Psi has either MF equals minus 1 and sigma plus, or it has MF equals plus 1 and sigma minus. Okay. Now this is the first stage of the experiment, I mean after trapping. The question is still, what does this help? After all, you were interested in entangling the atoms. And now, let me draw the whole setup. So here you have atom A, here you have atom B, and they are trapped. So they are held in a combination of magnetic field and optical laser fields in order to stabilize them there. Now you have these photons being emitted, and then there is a trick. So it is possible to place a beam splitter such that this pair of photons simultaneously impinges on the beam splitter. And then in a certain arrangement, which we will discuss a little bit later, you can register simultaneous clicks on these 2 detectors, and by registering the clicks, you project the photons in an entangled state. This is a certain kind of measurement, which is called measurement in a Bell basis of 2 photons. So for the moment, just trust me, you can, by registering an appropriate event, make sure that you project the photons on an entangled state. Now, of course, since the photons had to be entangled with the atoms, this then automatically also projects the atoms into an entangled state. And so that is the trick. Now, of course, there will be many events that don't lead to the desired state, but you just throw them away. So the idea is to run through this experiment many, many times, excite both of the atoms, register clicks here, and then just keep the correct events where you know that now the atoms must be entangled. And since this is stored in an internal hyperfine level of the ground state, these are fairly long-lived, and then you have enough time to read out the atomic state, and that you again do by spin-selective ionization. And so right now, as far as I'm informed, they're just testing all the different components, for example, this ionization and the optical link and so on. And so when they put all of this together, according to the numbers, they should easily be able to fix the locality loophole, and they also should easily be able to fix the detection loophole. And when this is done, I mean, you don't need any of these modified Bell's inequalities and extra assumptions. It's then just a complete violation of Bell's inequalities and ruling out local hidden variable behaviors. Okay. Well, so now we've discussed all these Bell tests. Let me move on to some other variations on those Bell tests and entangled states. And the first variation you can think of, or one of the variations you can think of, is just to have more than two particles. So the first authors to consider more than two particles in this context were Greenberger, Horn, and Zeilinger. And so the states that they considered are now called Greenberger, Horn, Zeilinger states. If we don't want to write that much, we abbreviate that by GHZ. So the idea is very simple, the state is very simple. One possible Greenberger von Zeilinger state is just the one where you take 3 spin 1/2 particles and you have them all either spin up or you have all of them spin down. Now, you immediately see this is an entangled state because there's no way you can write it as a product state. Now, you could go ahead and try to derive some kind of generalized Bell's inequality for this, but actually it turns out that once you have 3 particles, the contradiction is much more direct. It is as if in the 2-particle case you would have gotten a contradiction even for the case where you have the perfect anticorrelations. Of course, we know that the perfect anticorrelations are very easily explained in a local hidden variable model, but it turns out just such a direct contradiction can be produced once you get to 3 particles. So, just in order to reduce the writing effort, I just want to have an abbreviation, namely whenever I want to refer to sigma x, the x component of the spin, I just write x. Yeah? Xj would be the x component of spin number j. Now, all we need is, we need to know how sigma x acts on spin up and spin down, and we will also need how sigma y acts on spin up and spin down. So let us just recall this. We know, for example, if I apply sigma x to spin up, I just get spin down, so I flip the spin. If I apply sigma x to spin down, I just get spin up. Okay? Now, likewise, if I apply sigma y to spin up, I get I times spin down, so there's this extra I in here. And if I apply sigma y to spin down, I get minus I times spin up. Now, the fact that there's a difference in sign is simply because sigma y is a Hermitian operator. So the matrix elements have to be complex conjugate of each other. And the way I wrote it down here is compatible with the usual way of writing the Pauli spin matrices. If spin up is the state in my basis where it's the first basis state in my basis. Now this is just a detail. Now this is all we need, because then we can go ahead and we can apply these operators to our particular GHZ state. And the kind of measurement we will be interested in is of the type where, for example, we measure simultaneously all the x components of the three spins. So that would be sigma x1, sigma x2, sigma x3. And it turns out this is very simple, so that would be asking, what do I get if I apply x1, x2, x3 to my state psi? It turns out this is very simple, because it turns out psi is an eigenstate. Because I can flip all those up spins down, and I will flip all those down spins up, and then of course I get the same state. So I just get psi. Now I can also do more interesting combinations. For example, I can try to find out what happens if I apply y,y,x. Now here it's maybe not so clear immediately. But for example, take the first state. The up will be flipped to down and I get an extra factor of I. Again, the second up will be flipped to down, again I get a factor of I. And the final x operation will flip the last spin to down without any factor. So I get two factors of I, makes minus 1. Now for down and down, each gives me a factor of minus I, but the product again is a minus 1. So all I get is the whole state multiplied with minus 1. So again, this has turned out to be an eigenstate. And of course the same would happen if instead of y, y, x, I try to measure y, x, y, or x, y, y. Yeah? Okay. So far so good. So it turns out that instead of just having some statistical correlations, these are just eigenstates. So this product will always give plus 1. This product will always give minus 1 if I measure it. Okay. Now let's make a little table. And in writing down this table, I now want to imagine that if I write the operator without the hat, it is supposed to be the measurement result, because in the end I want to compare against local hidden variable theories, and local hidden variable theories don't know about operators, but they do know about measurement results. Okay. And the measurement result is plus or minus 1. And we want just to consider several measurement combinations, such as xxx or yx. And also note down the result that we expect from quantum mechanics. Okay, so the first combination would be x, x, x. And the result will always be plus 1. I mean, individual measurements could yield both plus and minus 1, but the product will always be plus 1. And so then if we measure y, y, x, we get minus 1. Again, y, x, y is the same, it's also minus 1. and x, y, y is the last one, is also minus 1. Okay. Now this seems harmless, until you ask about what would a local hidden variable theory predict. So local hidden variable theories would say that even before the measurement, both x1 and y1 will have some values. They are random from trial to trial, but they will have some values, and only then I will decide, do I measure rather x1 or y1 and so on, and of course we cannot measure both of them at the same time, but still, before the measurement, all of these numbers will have definite values. And so, what I can do is the following. I can take the product of all of these numbers here. So again, local hidden variables tell you that x1, x2, x3, y1, y2, y3 have definite values. And I want to take the product of all of these. Now you see, there's a funny feature of this product. For example, within the first column, there's x1 twice and there's y1 twice. And because x1 is either plus or minus 1, if I square it, it's always plus 1. Also in the second column, there's x2 twice and y2 twice. And again, the product will always be plus 1. So this product over all these four results, according to a local hidden variable theory, will be x1 squared, y1 squared, x2 squared, y2 squared, x3 squared, y3 squared, but this is simply plus 1. And you can readily see the contradiction, because in quantum mechanics the product is minus 1. So as I said in the beginning, this is really as if even on the level of these perfect anti-correlations in the two-particle BPR version, you would already have arrived at a contradiction with local hidden variables. And so here you don't need any complicated inequalities for correlation functions, at least at first. You do, however, have to make sure in your experiment that you really obtain these ideal values, because you don't know what is your state. Maybe you don't obtain these ideal values. So in order to derive a contradiction, not between quantum mechanics and local hidden variables, but between observations in a real experiment and local hidden variables, you still have to collect a lot of statistics and make sure that with practically certainty you always get plus 1 for xxx, you always get minus 1 for yx, and so on. So this contradiction, even on the deterministic level, does not mean that you would only have to run the experiment once. Because if you run it only once, you will just get, say, yx as a certain value, fine. Next time maybe you choose xxx as a certain value, but that was already the next attempt, the next value of the local hidden variable. So you still need to make sure that you always get plus 1 or always get minus 1. And then, of course, in reality, because of some misalignment of the apparatus, sometimes you don't get plus 1, sometimes you get minus 1. So in reality, you will still need to derive an inequality to really make sure that you have this contradiction. Okay, but this is still quite remarkable. So there's simply no way of making it work. So far we have discussed only these spin 1/2 experiments, or maybe horizontal and vertical polarization. So we have discussed qubit-like experiments where you have just these two possibilities. There's another class of experiments which deal with continuous variables. For example, continuous variables might be position and momentum of a particle, or they could be electric and magnetic field of some electromagnetic field. And you remember that the original Einstein-Podolsky-Rosen Gedankenexperiment was really about continuous variables, was about x and p. So for example, you remember the wave function for EPR. This was simply a two-particle state of this type that once you measure the position of one of the particles, you immediately know the position of the other one. And then we also rewrote it in the momentum basis, and we found also if you measure the momentum of one of the particles, you immediately know the momentum of the other one. And more generally, probably in a real experiment you can't produce this exact delta function, but you will produce states that approximate this very well, which if you plot them against the difference, they are very much peaked. Okay. Now, it turns out that, unfortunately, for this original EPR proposal, there does exist a local hidden variable theory to describe the results. And the reason is that you can actually construct a phase space density, that is a probability density for both x and p, or x1, p1, x2, p2, and it's a perfect probability density. And so instead of talking about some mysterious hidden variables lambda, these x and p's would be your hidden variables. And so in order to understand why this is the case, I want to have a brief excursion here and tell you, if you haven't heard about it, about the Wigner density. So the purpose of the Wigner density is just this, to provide the equivalent of a phase space probability density. And I just want to write down its definition for a single particle. So you are given a wave function, and you know the wave function is just a function of position, for example, or it's a function of momentum only, but it's not a function of both position and momentum. Still, you are interested in constructing something that is as close as possible to the classical phase space distribution that you know from statistical physics and classical mechanics, and that should depend on both position and momentum. And so Wigner figured out how to do this in the most reasonable way. So the result will be a density, let's call it W, of both position and momentum. And it's defined in the following manner. So there's a prefactor, not so important, 1 over pi h bar. And then there's an integral over position And basically it's a Fourier transform, but it's a Fourier transform not of the wave function, because that would be like taking the wave function from coordinate space to momentum space. It's rather a Fourier transform in the square of the wave function. So more precisely, it's psi star of x plus y and psi of x minus y. And then, since this is a Fourier transform in this coordinate y, you have to multiply by e to the I something times y, and the something is just the momentum. Okay. So essentially, x is like a center of mass coordinate, y is like a relative coordinate, and you Fourier transform in the relative coordinate. Now, this works not only for so-called pure states where I give you a wave function. We might also have situations where with random probabilities I give you different wave functions, in which case you would want to average over different wave functions. And the way to do this is to take this quadratic form of the two wave functions and average them. And then you would arrive at what people know as the density matrix. So it's just averaging over this random sample of wave functions. Okay. So the Wigner function is a very general description that at least gives you something that depends on the position and the momentum. What are its properties? It has many properties. I just list some of the most important ones. The first thing is it's real valued. This is of course very good. You can check it for yourself. If you take a complex conjugate, it's like having the complex conjugation on the second factor, not on the first, but you also have a different sign in the exponent, and then just by substituting in the integration y going to minus y, you can turn it into the same expression. So it's real valued. The second point is it's normalized. That means if you integrate over both position and momentum, you just get one. This is what you would expect if this is to be a probability density. Third, maybe you're interested only in the probability density for position, which of course you can obtain simply from the wave function by taking psi of x squared. But you can also obtain it by saying, I take w and I don't care about which momentum I have. So I just integrate over the momentum. And likewise, if you don't integrate over the momentum but over the position instead, you get something that only depends on the momentum, and this turns out to be the correct probability density in momentum space. And now, since this is true, then you can evaluate immediately any expectation value of the position or the position squared or any function of the position simply by multiplying that function with the Wigner density and integrating over both position and momentum. So, for example, integral dx dp f of x w of x comma p is really the same as taking the expectation value of this function of the position operator. And likewise for the momentum, and you can also work it out for more complicated combinations of position and momentum, but then you have to be more careful in constructing the function that you multiply with w. Okay, so you can get all your expectation values. Now what's the catch? And the catch is it can become negative. It can become negative bounds. So there is a nice bound. Minus 2 over h bar is smaller or equal than the Wigner density, smaller or equal than 2 over h bar. So it can become negative, but not infinitely negative. Maybe it helps to have examples. For example, if you take the ground state of a harmonic oscillator, it turns out that the Wigner, you know, the ground state of a harmonic oscillator is just a Gaussian wave function. Turns out the Wigner density is also just a Gaussian wave function. This is not surprising since here you multiply two Gaussians, get another Gaussian, here you take the Fourier transform, still get a Gaussian. So you have a two-dimensional Gaussian. So in X and P space, you just have this two-dimensional Gaussian function. But for example, if you pick the first excited state of the harmonic oscillator, automatically already you get negative values. So it looks like a crater, and then it has a dip down into the negative values. And the interesting fact is that whenever you have a Gaussian state to start with, like the ground state of the harmonic oscillator, then the Wigner density remains positive. So instead of the ground state, you could, for example, have a coherent state, which is just a displaced ground state, so it sits somewhere else in the phase space plane. Or you could have a so-called squeezed state, which really, in terms of this two-dimensional Wigner density, means you squeeze it in some directions, so you decrease the position fluctuations and you increase the momentum fluctuations. And then if you have two harmonic oscillators that are coupled to each other, you can imagine in the space x1, p1, x2, p2 some more complicated Gaussian state that does include correlations, but still it has a positive Wigner density. So all this formalism can also be applied for the Wigner density of two harmonic oscillators, or two particles in general. And the point I want to make here is that if it's Gaussian, if the wave function is Gaussian to start with, you end up with a positive Wigner density. And so if you go back to the original EPR suggestion, of course the delta function looks a little bit pathological, but if you replace it like this, or if you try to produce it in the typical setups, you always end up with a Gaussian state and you end up with a positive Wigner density. And then you can say, oh, this is just my joint probability distribution for positions and momenta of the two harmonic oscillators. And it's then very easy to describe all the measurements of positions and momenta according to this probability distribution. And for example, even if you're interested in something like not measuring x, not measuring p, but a linear combination of x and p, yeah? Like not measuring spin in x direction, not measuring spin in y direction, but measuring spin in z direction, that would be another example. So if you're interested even in these more complicated measurements, it's no problem, because physically you can get these more complicated measurements simply by having the particle freely move ballistically for some time. And you know that its position after some time is the initial position plus the velocity times the time. And the velocity is just momentum divided by mass. So any of these linear combinations of position and momentum can just be measured by a free expansion for some time. The free expansion in the Wigner density does not destroy the positivity, and so you don't get any contradictions. Okay. Now, what's the way out if you are interested in ruling out local hidden variable theories? Well, there's an obvious way out. It has to have to do with negative Wigner densities. And for example, you see one example of a negative Wigner density. It's just taking the first excited state of a harmonic oscillator, which in the context of quantum optics would mean a single photon state, for example. So then things are very different. Also, sometimes you can effectively produce such situations by not having such a state in the beginning, but by detecting, say, in a single photon basis and then post-selecting certain measurements. Okay. And so it turns out you can write down a Bell inequality that also works for continuous variables, but it does not work only on the simplest possible correlation functions, which would be like x1, p2, and so on. Because it can be shown that's just too simple. You can always reproduce any set of such simple correlation functions by having a positive Wigner density, and then obviously you have constructed a local hidden variable theory. So a Bell inequality for continuous variables has to involve higher moments, like correlating x squared for the first particle with p to the fourth for the second particle. So it has to involve both these higher moments and these more interesting states. And if you want to know more about it, that's a relatively recent development. That's a paper by Cavalcanti, Foster, White, and Drummond. Okay, so violating Bell's inequalities with continuous variables doesn't seem to be so easy, but you can have a more modest goal. You can say, well, let me pretend I do believe in quantum mechanics. Can I still check whether the state was entangled? Yeah? That's much more modest. You don't want to rule out all the local hidden variables, but you want to check whether at least I was efficient in my state preparation and still got an entangled state that is a good approximation to the initial EPR idea. Questions at this point? I mean, it's kind of ironic that the original EPR idea was then transformed by Bohm into the spin idea, which was then taken by Bell to rule out local hidden variables. And if you go back to the original EPR idea, you don't find such a violation, and you can't rule out local hidden variable theories. Okay, so let's briefly talk about this more modest goal of just checking that the state is entangled. Now, you know that the ideal EPR state has perfect correlations between the x and the p. So I can write this down in terms of variances. I can say, let me take the difference between x1 and x2, and then take the square, and this is just 0 in the ideal case, where this wave function was a delta function. And also we rewrote this wave function and found that also the momenta are perfectly correlated. There it was the sum that was 0. So I would write p1 plus p2 squared is also 0. Now this is the ideal case. Maybe you don't quite reach the 0, and you want to figure out when is the threshold, when things start not to be entangled necessarily. Now in order to compare this, we could say, oh, let's compare with an uncorrelated state. Because what happens if I take this difference squared in an uncorrelated state? Well, you see, there's this cross term x1 times x2, and if I average that, it will just be 0, assuming for a moment all my averages of x and p are 0 anyway. So then I will have the difference squared average is just x1 squared average plus x2 squared average, simply because this cross term x1 times x2 vanishes, because they are not correlated. And if I have p1 plus p2 squared, again, I would have p1 squared plus p2 squared. Now, in principle, of course, we can prepare states where, say, the x1 squared and x2 squared are both very small, to approximate 0, so to speak. But then, because of Heisenberg, automatically the p1 squared and p2 squared will be very large. So there must be some inequality that tells me that if the state is uncorrelated, then somehow the combination of both of these cannot possibly both be very small. And so that's the idea of trying to check for entanglement in these situations. And so the criterion I now want to write down, probably in its earliest version, was due to Margaret Wright and Peter Drummond, but the version I want to write down is from a paper by the Zoller group in 2000. Okay, and so they say, let's take combinations such as x1 minus x2 and p1 plus p2, but let's be a little bit more general, because we don't know what the state is like, and maybe the correlations are such that not x1 minus x2 is very small, but x1 plus x2 is very small, or some other more complicated linear superposition of the two. And so they want to consider everything. And they would introduce U is something like the X combination, but with arbitrary prefactor. So you have A being a real number, and then you take A times X1 minus 1 over A times X2. And V is just the same for the momentum. But you see with a plus, so it's just the opposite. And so A is just any real number not equal to 0. And so there's still one little trick here. In order to write down the inequality, I want to have that someone has made the x and p already dimensionless, which you can easily do. You can take your real position and divide it by something like the ground state width of your harmonic oscillator. It doesn't matter, because in the end you can always fix this by playing around with the A as a scale factor. And likewise, someone has turned P into a dimensionless operator, and so not only are they both dimensionless, but because of the x, comma p. The commutate is just I, not I times h bar as usual, but just I. And then they consider the following inequality. So variance of u plus variance of v larger than or equal to a squared plus 1 over a squared. And if this inequality is violated for any choice of a, then you're sure you have an entangled state. So you just have to try around with different a's because you don't quite know what is the type of entanglement in this initial state. Is it x minus, x1 minus x2 very small, or is x1 plus x2 very small? But once you find a violation, so the variances are smaller than the right-hand side, then you are sure it's entangled. And for example, for the original EPR state, you would just choose a equals 1, and then these would just be exactly 0. And then it's trivially violated. Okay, so this is the type of criterion that you would consider. Okay. Now, I basically want to end this chapter by telling you a little bit about applications of entanglement, just to show you that what had started as an investigation into the foundations of quantum mechanics has actually, well, say, it is now on the threshold of becoming useful. Because these applications are, of course, almost all of them not real-world applications yet, but in principle they are there. Okay. Now I've chosen a set of a few applications. Again, one could have a full lecture on all of this. The first application has nothing to do with quantum communication or quantum information processing, but it's actually about being more sensitive to small fields. So you would call it precision sensing. And, well, if I give you a spin and you want to measure a magnetic field, what can you do? You can just leave the spin there for a time, and the magnetic field will lead to a precession of the spin. So in quantum mechanical language, the precession of a spin is just described by the fact that the two states that have different energies acquire different phase factors. And the phase factor acquired during a certain amount of time is just proportional to the strength of the field. So if you are then able to measure that phase shift, you can measure the strength of the field. So if I have just a single spin and put it in a superposition of up and down, and I have a magnetic field which is switched on for some time, which provides an energy difference between these two states, then after a certain time I will get a state which can look like this: up plus e to the I phi of t times down. Yeah. Now I left out an overall global phase factor for this wave function, but this is the important part, the relative phase. Now of course you see that you can't possibly measure this phase only with a single spin, yeah, because you have to project it onto one direction and then the end result will just be +1 or -1. You never get a real valued number out of this measurement. So really you have to have many such spins, and then you measure them very often. And this is really what you do in NMR or electron spin resonance, because you have an ensemble of billions of spins in the material. Okay, or you just have to repeat the experiment many, many times. Now, how to make it more sensitive? Instead of just having many uncorrelated spins, for each of which you try then to measure this phase shift, you can actually do the following, and it turns out to be better. You can have one of those GHZ states, so you have up, 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 plus down, down, down. And then you can imagine very well what happens. So if for a single spin I get a phase of phi, then for this combination of 4 spins, I get 4 times phi. And so you have 4 times the phase here, and the real comparison then would have to be made in terms of fluctuations of the phase. And it turns out that if you just take 4 independent spins, you have larger fluctuations than if you have these 4 correlated spins in this 4-spin state. And so people have implemented that, for example, in optics, or well, they have taken this idea and carried it over to optics. It still has to be implemented, I guess. And the states there are called noon states. So this is a little bit of funny notation. What that means is the following. Imagine you have an interferometer with 2 arms, and in one of the arms you have some medium, maybe a gas of atoms or something like this, and you want to measure the phase shift very precisely. And so instead of just sending billions of independent photons through that system, if you are smart enough, you might be able to compare a state where either you have n photons in beam number 1 and 0 photons in beam number 2, or you have 0 photons in beam number 1 and n photons in beam number 2. And then you realize this is just the same situation. Yeah? So 1 and 2 are up and down, and so this is the same situation, and so all of these n photons will acquire exactly the same phase shift, yeah? Without any fluctuations. Now, there are many possible problems in this scheme, obviously. The biggest problem is probably to even create such a state in the first place, because it does not help if you just have a beam splitter here and then you send through n photons, because each of the n photons will have an amplitude of going through the upper or the lower arm, and then you get a very long product state, but not this mean state. Also, if you have prepared this, in the end, you somehow have to measure this phase difference here. And so in order to measure this, it's not good enough if you try to measure, say, the expectation value of sigma x1. Because if you take this state and work it out and calculate the expectation value of sigma x1, you will get just exactly 0. Because sigma x1 can only flip the first spin, but then there are all these other spins and you just get exactly 0. I'm sorry, at least you don't get any dependence on the phase. So what you really need is a measurement that is sensitive to the combination of all of the spins, and that would be something like a measurement of the operator sigma x1, sigma x2, x3, and x4, for some many particle correlation measurement. And then, even if all of this can be done, if it can be prepared and if it can be measured, the mere fact that it is so sensitive to any external fields, of course, also means that it is very prone to decoherence. Yeah? I mean, that's the general problem for any sensitive detector. If it is so sensitive to the very small fields, it's also very sensitive to very small field fluctuations. And so the same happens here. These states are very fragile, and so there are many calculations in the literature. What would this mean if I have some photon losses in this arm? How quickly do I degrade my state? How quickly does it become actually worse? than the usual scheme. Okay, but at least this is in principle an application of precision sensing. And maybe, who knows, maybe they will be doing it with ions. Okay. So today let me finish by saying something about quantum cryptography. The idea is that you use quantum mechanics to send a secret key between two parties, so that in the end they have a joint secret key, and then they can use that to encrypt some information. So the procedure is actually called quantum key distribution, because you distribute a secret key. Now, you can exploit quantum mechanics to do this, to do quantum key distribution, and the easiest method was invented by Bennett and Blassard, who said, oh, let's just prepare spins in a randomly chosen basis, like either it's up or down with regard to the z direction, or it's up and down with regard to a direction that is tilted. And then if anyone, and you send these spins to the other party, and you measure them at the same time, again with randomly chosen settings, and you keep in the end only those where the settings happen to be the same, because then they will be, say, anti-correlated or correlated. But if anyone tried to intercept the state, the problem is that the one trying to intercept the state does not know what is the correct basis to measure your state in, and then maybe does introduce some mistakes. Okay. So this is a scheme that only depends on the fact that in quantum mechanics, if I give you an unknown state, you cannot possibly find out the full quantum state, because you simply have only one possibility for a measurement, and then it's projected, and so by that you can't figure out the full state. So that was the original protocol, which has nothing to do with entanglement. Just mention it because it's the simplest one. Somewhat later, a few years later, there was another protocol proposed by Arthur Eckert, and this does make use of entanglement, and it does make use of Bell's inequalities. And so that I want to mention briefly here. So the setup is just the usual setup for a Bell experiment. We have a source, and we have A and B, Alice and Bob as they are called in this context. They share an entangled pair. That's the purpose of having this source. Now they are supposed to measure randomly along different directions. And so each of them actually now has 3 different directions, in contrast to the usual Bell test experiment where 2 would be sufficient. Each of them has 3 directions. And so, for example, A has 0 degree, 45 degrees, 90 degrees, and B has 45 degrees, 90 degrees, and 135 degrees. And so what will happen is that sometimes they choose by chance to measure along the same direction. And if this is a singlet state, then they will get perfectly anti-correlated results. And those results they take as the secret key. And sometimes they measure along different directions, and those results are also very worthwhile, because those results they can take to test for a Bell's inequality. And by testing the Bell's inequality, they can check whether actually anyone is listening in. So after having done all this measurement, they publicly announce which directions they chose to measure in. And then for all the cases where they chose the same direction, this defines the secret key, because they are perfectly anti-correlated. So for the same settings, you keep them and they are your secret key. And for the other settings, you try to apply a Bell test. And now what Arthur Eckert was able to show is that if there is really someone intercepting here, like measuring along a random direction and then registering the result and then resending a particle that has been newly prepared, you won't be able to violate the Bell inequality any longer, because it's somehow like introducing a local hidden variable. And so the Bell test here is becoming very useful just as a test to check for the presence of anyone eavesdropping on this communication. Okay. Are there any questions left for today? Well, if not, so see you on Monday.